Ok, podemos começar, Thiago?
Sim.
Hello, everyone. Welcome to this week's BRAG, Brazilian Algebraic Geometry Seminar. It is my pleasure today to present our speaker, Thiago Fassarella from UFF, who is going to speak on moduli spaces of parabolic Higgs bundles. Please, Thiago.
Okay, so thank you very much. I'm very happy to give this talk at the Brazilian Algebraic Geometry Seminar. So first of all, let me say that this is a joint work in progress with Frank Loray. And we are interested in the moduli space of parabolic vector bundles and parabolic Higgs bundles. So to begin with, let's consider a reducible smooth curve over the complex numbers of genus G, I mean a Riemann surface. And let's fix a set of n distinct points on X, and D is going to be the divisor defined by them. So along the talk, I will define this moduli space of parabolic vector bundles and Higgs bundles over this curve with marked points. And then I will introduce this notion of spectral curves and Hitchin fibration. And after that, we will discuss this correspondence between Higgs fields and line bundles with spectral curve. So this is a very nice and well-known correspondence, which has been introduced in these two fundamental papers, the one by Hitchin and the other one by Bovil, Narasimhan, and Ramana. So this is the first part of the talk, and I'd like to give a basic introduction to the subject. And there's a nice dichotomy in this for this moduli space. So here is the moduli space of Higgs bundles, and here is the moduli space of parabolic vector bundles. And there is a map which is the forgetful map, which forgets the Higgs fields. And the general fiber of this map, it can be identified with the cotangent bundle of the basis at that point. And on the other hand, the Hitchin map is the general fiber of the Hitchin map is a projective variety. I mean, in fact, it's an abelian variety from using this correspondence. This is an abelian variety, which is the Jacobian variety of the spectral curve. And the moduli space of Higgs bundle is actually, this is a symplectic variety, which extends the symplectic structure of the cotangent bundle of the moduli space of vector bundles. Then we get these two Lagrangian fibrations which have a complementary dimension. So the dichotomy, I mean, the forgetful map goes to a projective variety, and the fiber of the forgetful map is an affine space. The Hitchin map goes to an affine variety, and the fiber of the Hitchin map is a projective variety. Actually, it's an abelian variety. So in this talk, what we want to do is the following: we take a finite covering of X, and we want to understand the behavior of the modular map defined by this map with respect to the Hitchin fibration. So at the end of the talk, I will discuss the behavior of this modular map, and if I have time, I want to discuss an application to the elliptic cover, which was motivated by the paper of Frank Loray and Valente Mires. But their paper is more about connection. So here we are with Higgs bundles And then we can take advantage of the Hitchin fibration. So this is the idea, this is the plan of the talk. So let me start by saying what a parabolic vector bundle is. So a parabolic vector bundle is nothing but a holomorphic vector bundle here of rank 2 over X. And for each parabolic point, we take a linear one-dimensional subspace in this fiber. So this is how I visualize a parabolic vector bundle. In fact, this is the projectivization of the rank 2 vector bundle. So this is a irrelevant surface. And a parabolic Higgs bundle is a homomorphism with the coefficients in the sheaf of one forms with simple poles on D. Each is nilpotent with respect to that parabolic direction. And to be nil, I mean that the residual part of the Higgs field, which is an endomorphism of the fiber, the kernel of this residual part contains the parabolic direction, and the parabolic direction contains the image of the residual part of the Higgs field. So, in order to define a nice moduli space of parabolic vector bundles, we need to introduce a suitable notion of stability, and then to this we fix a weight vector A. This is just a sequence of real numbers between 0 and 1, and then there's a notion of slope with respect to this weight. So the slope of E is just the degree of E plus the sum of weights divided by the rank of the vector bundle. And the slope of line subbundle is the degree of this line bundle plus the sum of weights, but we consider only weights corresponding to directions which are contained in L. And as usual, we say that the parabolic vector bundle is a semi-stable if for every line subbundle, the slope of E minus the slope of L. And now for a Higgs field, we do the same. We say that the Higgs field is A semi-stable if we have the same inequality, but for every invariant line bundle under the Higgs field. By invariant, I mean this. So with this notion, we can define, now we fix an integer D, and we fix a weight vector, and we can define the moduli space of parabolic vector bundles, the moduli space of Higgs bundles, with this fixed degree, and then there's a weight chamber decomposition for the space of weights, and we can show that if we take two weights which are in the same chamber, then we get the same moduli space. And when we cross the wall for this decomposition, we will get either a birational model of the previous moduli space, or it can be a contraction. And also, we know that the locus of stable parabolic vector bundles is non-empty, then it is a smooth projective, smooth variety of dimension n minus 3 plus 4G. And for the moduli space of Higgs bundles, its dimension is the double of the dimension of the moduli space of bundles. Okay. Actually, I forgot to say the definition for the definition of these moduli spaces, we need a notion of S equivalence. So I decided to not say so much about this, but we will see some examples. So in this example, let's consider the projective line and let's fix the degree to be 0. We can show if the divisor is a divisor of 4 points on the projective lines, then varying the weights, we can get either the amplitude. It means that there is no semi-stable parabolic vector bundle with this weight. It can be just a point, or it can be a P1. Just to see what kind of variety you can obtain with this varying the weight. Now, if we take 5 points on P1, we can get all the other cases, but we can get also the projective plane, and for some suitable weight, for instance, if we take 1/2 for the first 4 coordinates, the corresponding moduli space is adapted to the surface of degree 4, which is the blowing up of P2 in 5 general points. Now, if X is an elliptic curve, I'm fixing the determinant to be trivial. And in this case, if there is no parabolic point, then the corresponding moduli space is just a P1. So just to give an idea. So there's no parabolic point, and over the elliptic curve, a vector bundle with trivial determinant line bundle. We can show that it is in this form, or when L is a line bundle of degree 0. But for the elliptic curve, we know that there are exactly 4 undecomposable vector bundles, which corresponds to the following sequence. And then what we need to do is, for example, if we take the composable vector bundle, the trivial vector bundle, we can think that this undecomposable extension is given by a cycle like this. So say that this is an E0, and for the trivial line vector bundle, it can be given by this. But if we multiply this cycle by an epsilon, we give the same vector bundle. And when we make epsilon goes to 0, this vector bundle, which is fixed, and it converges to the trivial vector bundle. So that's the idea. So for the S equivalence, what we need to do in order to obtain a Hausdorff space, we say that these 2 vector bundles are in the same class. Okay. Now,
why you said there are 4 vector bundles is 0?
Yes, because you can take the torsion of E0 by a torsion line bundle. A line bundle which is trivial. The square is trivial. Okay?
Okay, thank you.
So taking 1 point over the elliptic curve, we get, again, we get P1, but the difference is that in this case, there is an open set of stable vector bundles. In the previous case, all the vector bundles were semi-stable, strictly semi-stable, meaning that they are not stable. It satisfies the inequality, not the strict inequality. Okay. And finally, if you take 2 points on the elliptic curve, you can show that the corresponding moduli space is a P1 cross P1. So I could say more about this this moduli space if we take more points on the curve. And in fact, there's a very beautiful birational geometry behind it. But for this talk, I will just focus on these 2 cases. So let's fix the elliptic cover, and we can define a map at the level of vector bundles. We send the vector bundle over P1 with 4 points to the vector bundle over the elliptic curve, and we can define a map for the moduli space of vector bundles over P1 with 5 points, the moduli space of vector bundles over the elliptic curve with 2 points. Okay. So now let's go back to our goal. What we want to do, we start with a finite map between curves, and then we want to understand the behavior of the modular map defined by this finite map with respect to the Hitchin fibration. So the modular map, it is defined as follows. First, we take the pullback by a Higgs field on the base curve, and then we perform a split pole birational transformation, which is called an elementary transformation, in order to eliminate apparent singularities. Okay, so our next steps are the elementary transformations, and then the spectral curves and the Hitchin fibrations. Okay. So let's move to elementary transformations. So an elementary transformation is, from the point of view of the relative surface, it corresponds just to a flip, meaning that we fix a subset of D, the divisor of parabolic points, and the elementary transformation over this subset. To obtain the elementary transformation, we just blown up the direction, the parabolic direction. And doing this, there is an exceptional divisor, which is a Minor curve, but there was a zero self-intersection curve, which was the fiber, which is now a Minor curve. Then we can contract the Minor curve for the other side, and this gives a point. So this is a correspondence between relative surface with the marked points to relative surface with marked points. But we can do the same from the point of view of vector bundles. And the shift, the vector bundle E prime, which gives this relative surface, it is defined as the shift of sections of E, of those sections of E passing through the parabolic direction. And then we can check that this corresponding subshift gives this relative surface. So this correspondence between parabolic vector bundles gives a map between moduli space, but in order to preserve the stability condition, we need an appropriate modification of weights, and the elementary transformations will modify the determinant line bundle. So we need an appropriate modification of weight and also an appropriate modification of determinant line bundle. Anyway, this gives a map between a moduli space, and we can do the same for Higgs bundles. So in the case of Higgs bundles, the condition of the nilpotent condition implies that the transform vector bundle after the elementary transformation is invariant by the Higgs field. So it defines the restriction of the Higgs fields to the subsheaf, defines the Higgs field of this again, and then this gives a map also between the moduli space of Higgs bundles. So to give an example, let's consider the previous case. So S is a delta surface, which we see here, we see as the moduli space of the parabolic vector bundles over P1 with 5 points. And the P1 cross P1 on the target is the moduli space of parabolic vector bundles over the elliptic curve with 2 points. So the map between this surface, we take a point of S, which is a parabolic vector bundle, which is semi-stable with respect to this weight. And then here just to illustrate, I judge the trivial vector bundle. Then the pullback of this vector bundle is the trivial vector bundle over the elliptic curve. But to the stability condition, to preserve the stability condition, we need to multiply the weight by 2, because this is a 2 by double cover of P1. And we see that the weights, for this coordinates, all the weights is going to be 1. Then what we can do is the following: we perform an elementary transformation over the ramification points, and the weights is going to be 0. So this map, this modular map, this gives a map between a moduli space, and you can check that this map is a map of degree 2, and we can even explicit the involution of the map. So the deck transformation in the involution of this map is the elementary transformation over the branch locus of the finite cover. I mean, if you take a point which is a parabolic vector bundle, you perform an elementary transformation of the branch locus, and then you do the pullback, and you perform an elementary transformation of ramification points. At the end of the day, you get the same vector bundle. So this is really a very useful tool for studying this moduli space. And now, let's move to the Hitchin fibration, then to the spectral curves. We want to discuss this correspondence between the fiber of the Hitchin map and the peak variety of the spectral curve. So let's start by saying what the spectral curve is. So we fix the Higgs field, and this gives this section S. And locally, I mean, roughly speaking, the spectral curve is just the curve defined by this equation. So this is a 2-by-1 map. That's a double cover of this curve, which is ramifies over the parabolic points because of the condition of the nilpotent condition. But it may happen that we have more ramification points. The genus of the spectral curve can be computed by this equation. So, for example, if you take 4 points on the projective lines, then the spectral curve is a curve of genus 1. So, in fact, the precise definition of the spectral curve is the following. I do this because I will need the sequence. We fix the line bundle, say at O, which is this line bundle, and we fix a section of L and the section of L squared. So this section plays the role of the trace and the determinant of the Higgs field. Then we can define a structure of commutative ring on this OX module. So this is a OX module of rank 2, but we define the structure of ring using this section. And this gives a O algebra. And finally, the spectral curve is just the scheme defined by this algebra. And we can check that locally, the spectral curve using this structure, we can check that there is an isomorphism, and it then it corresponds to the previous definition, the local definition. Okay. To give an example, let's continue with P1 with 4 points, and let's take the vector bundle, the trivial vector bundle over P1, and I fix this set of eigen directions of parabolic directions. And what is a Higgs field in this vector bundle? So the Higgs field is just a matrix of one forms with simple poles on D, which satisfies the nilpotent condition with respect to the parabolic directions. Then we put all these conditions together, and we get explicitly equation for this matrix. And if we take the determinant of this gives the equation for the spectral curve. So this, as predicted, the spectral curve is on an elliptic curve. And I'd like just to observe that the determinant can be 0, but it can be 0 for split-bow vector bundles. So for some special positions for this direction. Okay. Okay, now we were talking about the curve of eigenvalues of the spectral curve, but why not consider the curve of eigenvectors? So it seems to be easier because this is a curve which is contained on the relative surface. And for instance, for a given point of x, we take the fiber and we can take the eigendirections of this endomorphism of the fiber. And they may naively believe that the spectral curve coincides with the curve of eigenvectors. But in fact, they are different. For instance, if the Higgs field is holomorph over Ti over a point, we can show that there are two different directions, eigendirections for this point. But the spectral curve is singular because the determinant has a double zero at this point. So they are different, but anyway, we can take advantage of this construction, and we can, instead of consider the projectivization of the eigendirection, we can consider the whole linear space, and given a point of, if I fix a point at on the spectral curve, it corresponds to the eigenvalue of the Higgs field. Then what we can do is the following: we can attach the corresponding eigendirection to that point. So this gives this construction gives a picture. I mean, for each point of the spectral curve, we attach the eigendirection to this, and we can construct a line bundle over the spectral curve. And this is exactly the Bouville-Neresima-Ramanan correspondence. And I would say, as usual, the BNR correspondence. So for each Higgs field, we can construct a line bundle over the spectral curve. But let's be careful, because, as I said before, if the Higgs field is holomorph of this point, instead of having one direction, we have two directions to that point, but the spectral curve is similar. So yeah, we will not have a line bundle over the spectral curve. In fact, this has generically it has a rank 1, but there's a fiber of rank 2. So this is no more a line bundle, but this is a torsion-free sheaf of rank 1 over the spectral curve. So that's the idea of this construction. And here is the precise statement of the correspondence. We fix a section, finite number of sections of some powers of L. And if we assume that the spectral curve is integral, so it can be singular, then there is a bijective correspondence between Higgs fields, I mean homomorphisms with characteristic coefficient Si, and torsion-free sheaves of rank 1 on the spectral curve. In our case, the rank is 2, and then the trace and the determinant determines the section S. So this is the correspondence. And then a nice consequence of this correspondence is that the general fiber of the Hitchin map, if the spectral curve is, for instance, if the spectral curve is smooth, then the fiber of the Hitchin map for the moduli space of Higgs bonds, we are fixing the degree, then over the spectral curve, we're fixing the degree of the torsion-free sheaves. If the curve is smooth, any torsion-free sheaf of rank 1 is a line bundle, then this gives a correspondence between the fiber of the Hitchin map and the Jacobian variety of the spectral curve. And here is precisely the relation between the degree of M and the degree of the vector bundle E. Okay, so let's continue. To give an example, this or in this case of P1 with 4 points, we fix this weight vector, and in this case, the moduli space of bundles has a dimension 1. This is a P1, and the moduli space of Higgs fields is a surface. And we can check that the general Hitchin fiber is an elliptic curve, which is the Jacobian variety of the spectral curve, which is the curve itself, because this is an elliptic curve, as I said before in that example. But I just observed that there is a special fiber. So if the section is 0, we can show that this special Hitchin fiber, which we call the nilpotent cone, in this case is a union of 5 components. And the first 4 components that we see come from that 4 strictly semi-stable parabolic vector bundles. Okay, so we can go to our goal. So let's fix a finite map of degree 2 between curves. And let me denote by B the branch locus of this map, and R will be the ramification locus of this map. And how we can construct our modular map. So our modular map, we will take the pullback. We start with the Higgs field on the basis X with this polar locus. We take the pullback by this finite map of the Higgs field. And then we can apply an elementary transformation on the ramification locus in order to eliminate apparent singularities. And at the end, we get a Higgs field on this curve of y, which has poles over the pre-image of T under P. So this is the modular map. And we can show that this modular map, it preserves the Hitchin fibration. So by restricting the map to a Hitchin fiber, we will obtain a map between abelian varieties. So the idea is to understand how this map looks like. So to answer this question, to understand the behavior of this map with respect to the Hitchin fibration, what we need is a dictionary for the pullback and for the elementary transformations in terms of the PNR correspondence, in terms of line bundles over the spectral curve. So here is the statement, the precise statement of the theorem. First, we can show that there is an etalmorphism of degree 2 between spectral curves, and the restriction to the modular map to a Hitchin fiber is just the pullback by this map, as you can see, up to a translation. So let me explain the statement with details in this picture. So this is the first part of the statement. So what you do is we do the following. We start with a Higgs field, say theta over x. By taking the determinant of this Higgs field, we can look at the spectral curve, the corresponding spectral curve. So this is a curve which ramifies over parabolic points. Then after that, we take the pullback of the Higgs field, and the pullback will vanish of order 2, because this is a map of the 2-by-1 map. So the corresponding spectral curve of the pullback Higgs field is singular over the ramification points. And by performing an elementary transformation of this Higgs field, we get this one, and we can show that the spectral curve corresponding to this Higgs field is exactly the resolution of singularities of that curve, of the curve on the middle. And then the idea, yes, and then to understand the behavior of this line bundle under the PNR correspondence, we need to understand the effect of the elementary transformation over the Jacobian of the spectral curve. I mean, first, we can show that if you take the line bundle over the spectral curve, we can think this line bundle as the bundle of eigendirections of the Higgs bundle. So if you take this line bundle, and then we take the pullback by this line bundle and apply an elementary transformation, we can show that this at the end we obtain the line bundle corresponds to this map is the pullback by C modulo a elementary transformation, which gives a translation by a sweet-pole divisor, which is exact with the divisor over the ramification points. In sum, the pullback map corresponds to the pullback by C, and the elementary transformations corresponds to a translation in terms of BNR correspondence. That's the idea. And how we can prove that we can understand the behavior of the elementary transformation with respect to the PNR correspondence. So to do this, we need to understand the correspondence from the algebraic point of view. I mean, what is a Higgs bundle? A Higgs bundle is just a vector bundle, which is an OX module of rank 2 with an extra structure, which is the Higgs field. To obtain a line bundle over the spectral curve, so the spectral curve is the scheme defined by this algebra. So this is the structural sheaf of the spectral curve. So to get the line bundle, we need to define a structure of AS module. So what we can do is the following: we take E, which is an OX module of rank 2, and then we use the Higgs bundle to define the Higgs field to define a structure of AS module on E. The fact that the line bundle over the spectral curve is just the same vector bundle, but with an extra structure which is given by the Higgs field. So now this is we can show that this is a OX, I mean AS module. So AS is the structural sheaf of the spectral curve. So this is an AS module of rank 1. And then, to understand the elementary transformation, we can see that the elementary transformation of this vector bundle is the sheaf defined by those sections of E passing through the parabolic point. So in terms of B and R correspondence, it can be translated in the subsheaf of M given by sections that vanish at W. So that's the idea. Okay, so this is just a sketch of the proof of the theorem. And now let's see how you can use this. This is just to say that the map, we have shown that the map between fibers is the pullback by C up to a translation. And here, this is the Hitchin error. So the pullback means a pullback by C, and elementary transformation means translation. And then the map or a map is just the pullback by C up to a translation. So this is interesting because we say that the map C is a unramified map of degree 2 in our case. So it does not have ramification points. And then using this, we can show that this map is an étale morphism of degree 2. So this is not a ramified morphism over its image, of course, because this variety can have bigger dimension. Okay, so now let's apply this result to this case where we have the elliptic over P1. So this is a 2x1 map which ramifies over, it's branched over these 4 points. So here is the ramification point. These are the factor points. And using this with this map, we define a modular map between a modular space of Higgs bundles. So we can go from P1 with 5 points, so this is 5 points, to the elliptic curve with 2 points. And over P1, the degree is fixed for the line bundle, so it implies that the determinant is fixed. But over the elliptic curve, the determinant will be fixed. And this modular map is the same as I said before, but in this case, we just we apply, we twist by something in order to reverse the determinant to be trivial. Okay, so it's the same map, but this is just to get the trivial determinant line bundle. Okay, so this is a map from here we have a variety of dimension 4. This is also a variety of dimension 4. And we can show that by restricting to reducible Higgs fields, meaning that they don't have a invariant linear subbundle, I can show that this modular map is a surjective Italic covering of degree 2 on the reducible part. So this means that every reducible Higgs field over the elliptic curve with 2 points is the image of exactly 2 reducible Higgs fields over P1 with 5 points. And we can, using the previous result, we can describe the restriction of this map to any Hitchin fiber, even for those fibers which are singular. In the Galois involution of the curve, as in the case of the Delpizzo surface, is the elementary transformation given by over the branch locus of the map. So in this set sigma is just to say that this is the set of Higgs bundles that become reducible after pullback. You can show that this corresponds to this set. Okay, so this is our application to this to the elliptic cover. And finally, here is a picture which summarize the statement in some sense, because what we have in this case on the the P1 side, we can see that the general spectral curve is a smooth curve of genus 2, and the fiber of the Hitchin map corresponds to the Jacobian variety of this spectral curve of genus 2, and the degree will be fixed to be 3 in this case. And on the elliptic side, the general spectral curve is a smooth curve of genus 3. And what we get, the fiber of the Hitchin map, because we are fixing the determinant, is the Pring variety of this spectral curve on the side. And our modular map is an Italic map of degree 2 between the Jacobian. So we have this family of Jacobian varieties of curves of genus 2 to this family of Pring varieties of curves of spectral curves of genus 3. And you can show that the locus of singular spectral curves is a union of 5 lines. So the idea is that so the spectral curve over P1 is a curve of genus 2. So this is a curve which ramifies over 6 points over P1. Then when you take one of these points and we allow that this point goes to one of the 5 points, this gives a spectral curve which is singular at this point. So we have 5 ways to do this. And this locus of the spectral curves is a union of 5 lines, and at the elliptic side is the same. And you can show that the singular Hitchin fiber is a union of 2 irreducible components. And the involution of the map, it sweeps these 2 components. And each one of these components will be sent under this map to the closure of the Pring variety over the elliptic curve, which is the fiber of the Hitchin map over the elliptic, the singular spectral curve on the side. So that's the picture that we have been discussing, and I didn't say, but we can consider the weight, and when we consider the weight, actually this modular map, it becomes amorphous, and we can determine the locus of the branch locus of this map in this case. Okay, so I'll stop here. Thank you very much.
Thank you, Thiago. Are there questions for Thiago? Thiago, there's something I got a bit lost in the. So in the end, you were mentioning the singular spectral curves. So what is the locus on the Hitchin, on the base of the Hitchin fibration? So
okay.
How do you find the locus of singular?
Yeah, so let me. I will try to explain with this picture. So the spectral curve is it looks like something like this: 1, 2, 3, 4, 5, and 6. The first 5 points are over the divisor D. And there is an extra point, this one, say this one, which is allowed to move. So the spectral curve is a curve of genus 2 over B1. It's a double cover of 6 points. Then what we can do is the following: we can, this extra point, it can converge to one of the other points in that ramification. And when we do this, what we get is a singular curve. So these 2 branch points are replaced by a singular point. And there's exactly 5 ways to do this, one for each point.
So it's always a divisor. You always get a divisor of.
On the Hitchin, yeah, it can be more complicated if you have more dimensions, but we always have a divisor. The Hitchin discriminant is always a divisor on the base. Yes.
Okay. Okay. Thank you. Are there more questions? So if not, let's thank Thiago again. And let me stop recording.